Staying with the type of mixing problems, we're going to make a slight change to the original problem we had, where the input flow rate and the output flow rate of the mixture, the brine solution, was at 6 liters per minute, so that we had an assumption of a constant volume. Now we slightly change the problem so that we alter the output flow rate so that it's dampened a little bit, so the output flow rate is not 6 liters per minute, it's 5 liters per minute. Then we can't have the constant volume assumption for this particular model, where we have a 1,000 liter tank. And we're interested again in modeling X of T right here, which is the amount of salt that's in the tank at any time T. We'll keep the assumption that initially we have pure water or no salt into the tank before the solution starts entering. But now, given the difference between 6 liters per minute coming in and only 5 liters per minute going out, those two difference in rates really means the volume of the fluid in the tank after T minutes would be 1,000 plus T, because every minute we're gaining another liter of water. So what changes in this particular model for modeling the differential equation to model the change in the salt content, which we had earlier, remember, is the input rate minus the output rate, where the input rate was 0.6. That will stay the same, but the output rate now will change. So let's look at this particular problem and see how that would change. So again, we have dx dt is the rate change of the salt content, is 0.6, which we get by the product of 6 liters per minute times the initial concentration, 0.9 kilograms per liter. But now we'll be subtracting an output rate, which is now slightly different. So the difference is that now on output, we have the output rate of 5 liters per minute being multiplied by the salt concentration. But how do we do that now? Well, we know now that as per minute, we already represented the volume of the fluid is, so now the volume of the fluid is 1,000 plus T after T minutes. And of course this is kilograms per liter. And when we multiply that out, what we now have is the quantity 5 times X of T, or 1,000 plus T. And this would be kilograms per minute. And so this is the term that goes in the output rate, this particular model, where the output rate is not equal, it's less than what we're entering, so we can see the tank is actually going to fill with water and increase through time. So this is the differential equation we want to solve now, and so we could rewrite it a little bit, so we might recognize a particular form. So let's rewrite it here as dx dt equals to, let's pull this, since this is subtraction, let's pull it over to the side and write it as sort of this way: dx dt plus 5 times x of t over the quantity 1,000 plus t times x, x of t, right, is equal to the 0.6. Okay? So this should look familiar. This could represent, for example, q of t, the independent variable now is time t, and this component right here in front of the x of t certainly looks like a p of t function. So what we have, in fact, is a linear differential equation. And, of course, we need the integrating factor. The integrating factor in this case, mu of t, again, we're going to use t as our independent variable rather than x, would be e to this integral, and we could write it as 5 on the integral of dt over 1,000 plus t, because we pull the 5 out. So that, in fact, is just e to the 5 times the natural log of absolute value of 1,000 plus t. And again, we don't use constant for the integration factor. And realizing, of course, that time is going to be positive here. In this case, marching from 0 forward, we can drop the absolute value signs, and so we have e to the natural log of the quantity 1,000 plus t to the 5th power, using property of exponents. And of course, now we know e to the ln of something is just that exponent, so what we have is the integrating factor must be 1,000 plus t to the quantity of the 5th power. Okay. So then immediately we can use the form for solution then. We know then that x of t must be 1 over the integrating factor, which we'll write it as 1,000 plus t to the minus 5th power, because we're going to take that to the reciprocal, multiplied by the integral of q of t times the integrating factor, so that's going to be 0.6 times the quantity 1,000 plus t to the 5th power dt. Again, this is the Q of t term, and this, of course, is our integrating factor. Okay? All right. So if we just quickly evaluate that integral, what we're going to get, of course, is that this is equal to 1,000 plus t, the quantity minus 5, times 0.6, and then integrating that term, we get 1,000 plus t to the 6th power over 6, and then plus a constant. Okay. Right. And just with a little simplification, a little algebra there, we can show that x of t in this case would turn out to be 0.1 times 1,000 plus t plus that constant integration times 1,000 plus t to the minus 5th power. And recall that we had initially pure water, so we know this initial condition holds that x is equal to 0. So then we could say, well, that means then that 0 has to be 0.1 times 1,000 plus 0, which is just 1,000, plus c times 1,000 to the negative 5 power. And what we'll end up showing to solving that is that the constant would have to be negative 0.1 times 1,000 to the 6th power. So the amount of salt then for this particular model that's in the tank at any time t is given this quantity, 0.1 bracket, let's say 1,000 plus t, parentheses, minus 1,000 to the 6th power times 1,000 plus t to the negative 5 power. And that describes the amount of salt at any time t. So that if you needed the salt concentration, then salt concentration at time t, you just take this x of t for this model and divide it by 1,000 plus t, because remember it's initially you're gaining a liter per minute because of the difference in flow rates, and that would simplify out to 0.1 times the quantity 1 minus 1,000 to the 6th power times the quantity 1,000 plus t to the minus 6, and that would be kilograms per liter. So what's interesting here is if you look at the limit here as t goes to infinity here, what you can see is that the salt concentration is going to approach, is essentially going to approach 0.1 kilograms per minute, okay, in the limit. But, which is interesting because keep in mind that is exactly the concentration that we started with in a particular problem up here. But the difference between this model and the other, through time, as t goes to infinity, you're gaining this much fluid per time t. So as t goes to infinity, eventually your tank is going to overfill. So the tank will overflow at some point in time. It's like you're leaving the spigot running. You're not draining it out last night. The tank will overflow, but you will be overflowing with the concentration that you started with, 0.1 kilograms per liter. So this is a different problem with a different constraint in the beginning. You can also change the problem where the input rate is not the same. Either way, you're either solving with differential equations, either separable, or in this case, linear.